Good morning and welcome to Analog Electronic Circuits. This is lecture 12. So, in the last class, we basically concluded by saying that we know that in principle the transconductance of a MOS transistor operating in saturation I think I have been using the notation small v capital Gs. In principle, that Gm can be as large as possible, right. So, a MOS transistor operating in saturation behaves like an incremental voltage controlled current source, where in principle that transconductance, which relates the incremental drain current to the incremental gate source voltage, can be as large as possible, because in principle we can burn arbitrarily large amounts of current in the transistor and therefore get a large GM. All right. In practice, of course, as several of you pointed out, I mean there are real problems in the sense that the transistor may get too hot and may burn and so on, but they are what we would call practical problems. In principle, you can still have as large a transconductance as you want. So, using this as a building block, let us now try and build the 4 controlled sources that you are familiar with from basic circuit theory, right. The voltage controlled voltage source, the voltage controlled current source, the current controlled voltage source, and the current controlled current source. We will start with the voltage controlled voltage source, and because we are talking about incremental signals here, these the voltage controlled voltage source is basically going to be an incremental voltage controlled voltage source. Okay. In other words, the control source is a linear element, okay, and the transistor as such is nonlinear. So, we can only talk about incremental signals. So, any building block that we come up with using transistors which claims to be linear is only linear for small signals, right. That is understood. Now, let us recall what is the input impedance of a VCVS. Infinity. Output impedance is 0, and therefore, when you say we want we have a voltage controlled voltage source, the only number you have to specify therefore is the gain between the output and, so VO by VI is the gain, correct. Now, let us choose the simplest case, namely VO by VI is equal to 1, all right. We will reflect on why we chose 1 later on, but at this point 1 is as good as any other number. So, let us try to implement a voltage controlled voltage source with a gain of 1, and what we like to do is to make we also recognize that the transconductance, while it is large, is actually quite dependent on the operating point and threshold voltage and all this other stuff, correct. So, what we would like to do is to build an incremental voltage controlled voltage source, where the properties of the VCVS are largely independent of the properties of the transistor. In this case, the only property we are talking about is the incremental, is the transconductance of the transistor, all right. So, in other words, again let us derive this from first principles. We are what do you call the first, and as usual what we are going to do is basically first come up with a plan that we verbalize. Once you know what you want, you can always build an electronic circuit to do it, right. So, the problem statement therefore is we have a voltage Vi and we have some load resistance RL, and we would like the voltage across the load, which is VO, to be equal to Vi, and that is because we wanted to shoot for an incremental gain of 1, all right. So, let us imagine you are in a lab, okay, and let us for argument's sake also assume that there is some source resistance for the input, right. So, this is our source. We have a voltage Vi with an internal resistance of Rs. We are in a lab, we would like to make the voltage across a load RL exactly equal to Vi. Okay. So, in principle what would we do? What all equipment would we need? Okay. So, let me let me kind of track back a little and say, well, you want Vi equal to Vo, why not I just short Vi with Vo? Is this a smart idea or a stupid idea? Why? Oh, well, that's a terrible idea, because there is of course a voltage drop, and as you keep changing RL, the voltage will keep changing at the output. So, that is no good, right. So, we can dismiss that right away. So, what we need therefore is what do we need? Okay. Okay. So, basically one way of doing this is to say, well, we have a variable voltage source, okay, all right, and what do we do? Connect which with okay. So, basically the idea is to say, well, take a voltmeter which measures say the voltage between the positive terminal and the negative terminal, okay. And now what do we do? You read the the reading on the voltmeter, correct. And what is the reading on the voltmeter? What is the, by the way, what is the impedance of the voltmeter? If you have an ideal voltmeter, the resistance of a voltmeter is, internal resistance of a voltmeter is infinite. So, what exactly, what is the voltmeter actually measure? The reading on the voltmeter therefore represents, very good. So, the voltmeter therefore reads Vi minus Vo. So, if the voltmeter reading is greater than 0, what does it mean? What does it mean? Then we figure out what to do. It means that, I mean, Vi is what Vi is. You can't say it is too little or too high. It is Vo's job to follow Vi. So, it basically means if Vi minus Vo is greater than 0, it means that V naught is too small. What must I do therefore? Must increase Px. All right. Okay. Now, let me ask you a question. If we want to increase the potential of a node, in this case Vo, we are taking a variable voltage source and simply yanking its potential up and down. Can you think of another way of increasing or decreasing the potential of a node without using a voltage source? Yeah. So, there are two ways of changing the potential of a node. One is of course you use a variable voltage source to go and move the potential up and down. The other way is to pump a current, all right. And why are we interested in pumping a current? Because our transistor is it's a variable, I mean it's an electronically variable current source, correct. So, so therefore, we like to use a variable current source because we are talking about eventually using transistors. So, okay. So, now if we wanted a variable current, so instead of using a variable voltage source here, if you had to use a variable current source, what would we do? So, basically you need to connect a current which pumps current there, some Ix, correct. So, if Vi, if the voltmeter reading is greater than 0, it means that VO is too small again, but what must we do now? So, what we must do therefore is to increase Ix. Does that make sense? Alright. Now, if on the other hand Vi minus Vo is less than 0, what does it mean? What does it mean? V naught is too large, and therefore we must reduce Ix. Does it make sense, people? All right. So, therefore, we can see that Ix is the current source which is controlled by which voltage? Vi minus V naught. So, it is controlled. So, it is therefore proportional to Vi minus V naught, all right, and the constant of proportionality will therefore, the output is a current, the controlling quantity is a voltage. So, the constant of proportionality will have dimensions of conductance, right. So, and so that is what we will simply call GM, correct. Is the sign of GM positive or negative? Why? If Vi is greater than V naught, Ix must be positive, right. So, all right, okay. So, in other words, and remember that the general notation for a current source is actually that, all right. So, now can somebody recognize the transistor? The terminals of the transistor in this picture. Oh, by the way, basically Ix produces a current which is proportional to Vi minus Vo, and what if you want Vo to be exactly equal to Vi, what comment can you make about the transconductance Gm? How much do we need? Why? Exactly. So, you ideally want Gm must tend to infinity, because even if you see an infinitesimally small difference between Vi and Vo, you must go and kick that node Vo so hard so that its potential becomes exactly the same as that of Vi. Is that clear? All right. So, now what comment can you make? Can you now recognize the terminals of the transistor here? Stare at this picture. I mean, in this picture, this is the gate, this is the source, this is the drain. So, stare at the two pictures and tell me which terminal is which. So, the gate is the input, the source is the output, and the other end of the current source is drain, right, because you simply recognize this as being the incremental VGS. Does that make sense? And therefore, the circuit, when you recognize the transistor, becomes Vi Rs this is RL, this is VO. All right. Okay. So, let us tabulate the properties of the voltage controlled current. This is the incremental picture. Okay. it does not mean that, again let me reiterate that it does not mean that you take a transistor, connect it up like this and magically you will get VO equal to VI. This only works when the transistor is operating in the saturation region. So, for that you have to appropriately bias the transistor. You already know at least 5 or 6 ways of biasing the transistor. You can pick your favorite way. You bias the transistor. Once you bias the transistor, you also know how to get rid of elements that you want, that you do not want, and keep elements that you want, and so on, by adding infinite inductors and infinite capacitors, correct? And then you must make sure that your incremental circuit looks like this one, okay. All right. So, before we actually build the real circuit, let's tabulate what we will get as far as the input impedance is concerned. What is the input impedance? This is infinity, because the incremental gate current is 0. Does this depend on GM being infinite or not? That is independent of GM, correct? What about Z out? No, GM is infinity. Why? Yeah, the easiest way is to figure out that, well, if you go and change RL, what comment can you make about the output voltage? It remains the same, all right, and therefore, this basically means that the output resistance seen is 0 if GM tends to infinity. What comment can you make about VO by VI? This we knew already. If GM tends to infinity, the incremental gain is 1. Does that make sense, people? All right. So, now, so ideally GM must be infinity. In reality, well, we can say we can't get GM as infinity after all. GM must be very large. Now, the question is, yeah, so what is a large GM? All right, again, this is context dependent, and we have to figure out what the context in this particular case is. And how do you propose to figure out what it means to have a large GM? How do we figure it out? We know that GM must be large. Huh? Any ideas? Okay. So, so equivalently, you can say that there are multiple ways of doing this. One is to simply compute VO by VI when GM is finite, right, and stare at that expression and figure out for what values of GM that expression will tend to 1, all right. And to do that, well, we go back to our circuit here. This is GM times VI minus VO. What are the unknowns? What is the incremental gate voltage? VI, that there is no. So, what is the only unknown? VO. So, how will you figure out VO? Write KCL at the output node. So, VO by RL, that is the current flowing downwards, is nothing but GM times VO VI minus VO, and therefore, VO by VI is nothing but GM RL over 1 plus GM R. All right. So therefore, staring at this expression, what comment can we make about what constitutes a large GM? GM RL must be much greater than 1. All right. Or equivalently, the meaning of GM, a large GM, is that it is much greater than 1 over R. Okay. So, to find output impedance, so this is the gain with the finite GM. What comment can we make about the output resistance? How will we figure it out? How will we find out the output resistance? Well, we de-energize all the independent sources. So, Vi becomes 0, all right, and so therefore, does Rs and we need to find Z out. So, what will we do? We will replace the transistor with its incremental equivalent. So, that is our control source friend right there. We will put a test voltage and measure the test current. What is that? What is the strength of that current source? What is the strength of that current? So, what is that current source? GM times is the incremental VGS. What is the incremental gate voltage? 0. So, that is basically GM times 0 minus V test, right. So, that is equivalent to changing the direction of the arrow there and making this simply GM times V test. So, what do we conclude therefore? What do we conclude? So, our output resistance is therefore 1 over, and this is GM RL over 1 plus GM R. I mean, another way of doing it without doing this is to basically see that VO can be written as RL by RL plus 1 over GM times Vi, and simply staring at this expression, does this seem familiar? It is a voltage divider. So, the vertical arm is RL, the horizontal arm is 1 over GM and is being driven by a voltage source Vi. So, it is clear that this must be the output resistance. Okay. I mean, if you can see it this way, well and good. If you can't, never mind, it is not important. The foolproof way of finding output resistance is simply what do you call, de-energize all independent sources, which means that you short all the voltage sources and open all current sources, okay, and then apply a test voltage and measure the test current. That is something that will always work. Okay. So, with this, everything that we need to figure out about the amplifier is known. So, basically, let me redraw the circuit. this is Vi, this is Rs, okay. And as you can see, which terminal of the transistor is common to both the input side, to the input source as well as the load? The drain, right. So, what would you call this? This is the common drain amplifier, right. And the common drain amplifier is a way of realizing an incremental voltage controlled voltage source with a gain of 1.